bosonization. So we now have under control all the ingredients of the string worldsheet. Let's list them out. First, there are the worldsheet scalars. There's x. Then, and now we'll write down, there's mu. Mu runs from 0 to 9. Okay. Then there's the worldsheet fermions. There's psi, which is also mu. Mu runs from 0 to 9. Now, we decided, we went to Euclidean space, so let's say mu runs from 1 to 10. Okay. And we paired these psi mu's into psi 1 plus I psi 2 and psi 1 minus I psi 2. Psi 3 plus I psi 4 and psi 3 minus I psi 4. Okay. So, which we called e to the power I h1 and e to the power minus I h2. Bosonization. Okay. This guy is e to the power I h2. This guy is e to the power minus I h2, and so on. Okay. So we have 5 bosons, h1, h2 up to h5, that we can use in place of these 10 fermions, both separately on the left and on the right. This is one of the ingredients of the string worldsheet. Then there was the BC system, which if we want to, we could bosonize, but there's no real advantage to that, and we'll just leave it as it is. Okay. Then there was the beta gamma system. And the beta gamma system we did bosonize, and there will be an advantage to that. So let us recall, we had, somebody needs to help me, beta was equal to e to the power minus phi times del gamma was equal to e to the power phi eta, something like this?
Yes.
Okay. And in all of these discussions, phi of z, phi of 0 is equal to minus log z, hi of z, aj of 0 is equal to delta I minus delta aj log z. Okay, great. Now, what we're going to do now is to define this thing that we're going to call worldsheet fermion number. Okay. So let's first do it in the matter sector. In the matter sector, worldsheet fermion number is just the number of left moving fermions. Now actually we're not really interested in the worldsheet fermion number itself, we're interested in the operator minus 1 to the f left. So I'm going to talk about the left moving part for most of this lecture, then we'll, at some part in the lecture, we'll have to put the left and the right together. But unless I specify, it's left moving. Okay, so we are interested in this operator minus 1 to the power f left. Okay, and for that purpose, a good definition goes as follows. Suppose I have you see, e to the power ih and e to the power minus ih both contribute minus 1 to the power f left is equal to minus 1, because the definition of minus 1 to the f left is that the fermions should be minus 1 under this, but 2 fermions should be plus 1. Okay, so suppose I've got the operator e to the power I sum over alpha m h m. You know, so a good definition of f left is simply sum over n alpha m. And therefore, minus 1 to the power f left is minus 1 to the power sum over m alpha m. Is e to the power I pi times sum over m. right? So for instance, if we take alpha m is defined here. Suppose I have an operator here of the form e to the power I alpha m hm, where h's were these bosonized fermions, the bosons associated with the fermions. Okay? I emphasize I'm only really, this f left is going to have no interest for me. What's going to be of interest to me is minus 1 to the f left. I'm going to define f left for the purposes of defining minus 1 to the f left. Okay? So I want something so that minus 1 to the f left will evaluate to minus 1 for every fermion operator and plus 1 for every bilinear fermions. Okay? It's clear then that if you've got an odd number in these alphas, the net number of, when you sum up all the alphas, that thing something odd, then it has minus 1 to the f left equals minus 1. If it sums up to something even, it's minus 1 to the f left is equal to plus 1. Okay? So this sounds like a reasonable definition. Take f left to be the net translation charge for simultaneously translating each of the 5 HMs. That's some charge. I'll call that charge whatever it is, e to the power I pi times that charge. I define as minus 1 to the power f left. So this is my definition. And now that I have this definition, I've been careful to define it in terms of a conserved charge. Okay? I'm going to take this definition seriously and use it also in the Raman sector. Use it also in the Raman sector where things may or may not turn out to be integer. Okay, this is my definition. Minus 1 to the power f left is this object. For this operator? At the moment in the matter sector, yes. So for this operator, and then any dressing of del h's after that doesn't change it. It's just a translation charge. So minus 1 to the f left is the translation charge in the h's. Is this clear? Now x does not contain any does not contribute to minus 1 to the f left. Psi does in this particular way. Okay, great. Now BC also does not contribute to minus 1 to the f left because BC has nothing to do with the fermions. But beta gamma will. We need to define the fermion operator so that beta gamma also carry fermion number of at least minus 1 to the f minus 1. Why do we need to do this? Again, the ultimate reason here is that we're trying to define some sort of symmetry that will commute through the BRST operator. Okay? And you will see that our BRST operator has terms like gamma times TF. TF is odd in fermion number. So gamma times TF then would have to be even under this minus 1 to the f left, and that will only work if the beta gamma system, the beta and gamma also have minus 1 to the f left equals minus 1. Okay? We don't want to define as you will see, what we're going to do is take our theory and mod out by some symmetry. Okay? That symmetry should be something that goes through the BRST operator. Because in string theory we have the theory of the worldsheet and then we have the BRST operator. Okay? The theory of the worldsheet is often very simple, it's just a free theory. All the really interesting space-time physics comes from the BRST operator. Gives you the equation of motion in space-time, for instance. Right? So the BRST operator plays a key role, and any modding out should be something that is respected by the BRST operator. So this is basically the reason why we are forced to assign, if we're interested in a symmetry that will commute not just with the dynamics on the worldsheet, of which there's plenty because it's a free theory, but not just on the dynamics of the worldsheet, but also space-time physics. We needed to go through the BRST operator. Okay? So
at the level of Lagrangian, before you gauge fixed,
yes.
Beta gamma came from a Fermionic gauge fixing.
Right.
And BC came from a bosonic gauge fixing.
Right.
So at that level, if you want to define something that counts the fermions, then you would have defined.
You would automatically have done this.
Automatically, you would have given this to beta gamma.
Exactly. Exactly. It's basically minus 1 to the f left would be whether there's an odd or even number of fermions in the game. And some of these fermions could have been the spin 3/2 field of the gravity multiplet. So from that point of view, it would have been automatic. But since we're not going through this route, the remnant of that is the BRST operator.
Yes.
Okay, so that's how it's remembering what Indranil said. Exactly. So we need to enlarge our definition of -1 to the f so that beta and gamma also carry -1 to the power f is equal to -1. Okay, so, but you see, these guys also carry integer units of this phi charge. So we're going to enlarge our definition. Suppose this is this plus a phi. Okay, we will define our -1 to the power f left to be this plus a. Okay, so accompanying a shift in h by an imaginary shift in phi. Shift of 1 in h is accompanied by a shift of I in phi. Okay, so it's this.
I'm just confused about this. So this is an overall I pi outside or in the over here?
Here it's overall.
It's an overall.
Yes, it's just -1 to the power this. Is this clear? This, okay, this is our definition of -1 to the power FL. And it's a definition, we haven't yet studied the BRST charge for the superstring, that will be the next topic we study. But it's a definition that is chosen carefully so to ensure that the BRST charge, BRST current carries -1 to the power F1. The BRST commutes with this -1 to the F. Which one? Zeta gamma has nothing. So all of the charge here lies in the phi sector. So these guys carry -1 to the F0. Okay. Now that we have got this nice symmetry in our hands, okay, now that we've got this nice symmetry in our hands, what we're going to do is to try to, we're going to try to solve the problem of the tachyon. So what we're going to do is to try to take the Worldsheet theory and mod it out by some symmetry. Also, okay, and the way we're going to do that is, in a very pedestrian manner. So you see, suppose we've got the left moving side. There are two quantum numbers that tell us what kind of left, what the left moving side looks like. Okay, so I should say one more thing. The way, let us remember that, let us remember what the ground state vertex operator in the Raman sector was. Let's remember what the ground state operator in both the Raman and the Nebel-Schwartz sector was. In the NS sector, the ground state operator on the matter side was just 1 identity, and the ground state operator on the beta gamma side, and then maybe you want a C, so let's put a C. There'll be a C from the ghost system. From the beta gamma side, we got an e to the power minus phi. Okay, so the ground state operator in the Nebel-Schwartz sector was e to the power minus phi. What was the ground state operator on the Raman side? Well, there's always the C, plays no role. Yes, then we had e to the power I SAHA, where SA is what, plus minus half.
Yes.
Okay, and then there was e to the power minus phi by 2. It was e to the power minus phi, right? I haven't messed that up. Not plus phi. E to the power minus phi by 2. Right, correct. Okay. And then in the Nebel-Schwartz sector, we build on this ground state by acting with psi oscillators. Notice, therefore, that by our definition, the Nebel-Schwartz vacuum
There was no zero bond associated with zeta eta.
with zeta eta, there was, but you see, it was killed by a condition that we demanded that beta 0 annihilate the vacuum. There was this infinite dimensional phase space, and then we completely fixed one state in that by that condition. Yeah. Okay. Good. So the important point to notice here is that the Neveu-Schwarz vacuum carries minus 1, according to our definition, carries minus 1 to the power f equals minus 1. Okay. What about the Raman vacuum? Now, this thing can evaluate to any half integer between 5 by 2 and minus 5 by 2. Could be 5 by 2, could be 3 by 2, could be half, minus half, depending on details. Okay? And then there's a minus 5 by 2. The first, one thing I want to point out is that though it was not completely obvious from the way we did the calculation, this thing also carries minus 1 to the, fermion number, which is an integer. Because the halves in the H sector cancel the half in this sector. And then precisely what the fermion number of the state is depends on the values of SAs. So for instance, suppose all SAs were plus 1, but plus half. Then this would carry minus 1 to the power f positive. Suppose all SAs were minus half, then it would carry minus 1 to the power f negative. Notice that if an even number of SAs were positive, it would carry minus 1 to the power SA positive.
Even. Yes, it's positive.
But if an odd number of SAs is positive, then it carries minus 1 to the power SA, minus 1 to the power f left, negative. Okay, let's take an example. First we did all SAs positive, we got 5 half minus half, so that was 2, so minus 1 to the f left positive. Now let's take an odd number positive. Let's say for a positive, I said it wrong. I even said it wrong. When an odd number was positive, we got minus 1 to the power f positive because 5 half minus half. So I interchanged. When an odd number of SAs is positive, we get minus 1 to the f plus. When an even number is positive, we get minus 1 to the power f minus. Let's try. Let's say 4 are positive. Therefore 1 is negative. So the sum is now 3 halves. Because half plus half plus half plus half minus half. 3 halves minus half is minus 1. Okay? So even number of SA positive is minus 1 to the power f is equal to minus 1. And odd number of SA positive is minus 1 to the power f is equal to 1. By the way, this business came from quantizing the zero modes of the fermions. And quantizing the zero modes of the fermions made what representations of SO10?
You want product all of the.
When we quantized the zero modes, we had psi 0 mu, psi 0 nu.
They are fermion. They are spinor representations.
Yes.
And then you want to take direct product of the spinor representation.
No, just the spinner. I just want the representation that you get by quantizing the zero modes, which is the spinner.
Yes.
Notice though that SO10 spinor representations are reducible. They break up into chiral spinners and anti-chiral spinners. That's true of every even dimension.
Yes.
Okay? When is a spinner a chiral spinner? Well, depending on your notation, what you mean by chiral and anti-chiral, but let's say if all are positive, let's call that chiral. All are positive is 5 positive, or therefore any odd number positive is chiral. A chiral spinner is a spinner in which the highest weight vector is all pluses, and then you flip 2 at a time.
Don't you have to check that this is the closed set? You don't want you want your Lorentz group representation of the logarithm group in finite dimensional Hilbert space to break into two direct sum, right?
Yes.
So these vacuums are not mixed.
Well, yeah. All right, this does it, and how do I know that this does it? It's because, suppose I define, it's from -1 to the f. Suppose I define an operator such that every gamma carries -1 to the f1, because generators of the Lorentz group is bilinear in gammas. Lowering operators don't change -1 to the f. So within a chiral spinner, you don't change -1 to the f. So you only flip pairs. Okay, however you understand your chiral represented, it's yeah, it's fine. So if you just go and look up what a chiral spinner is or an anti-chiral spinner is, okay. Another way of saying it is that chiral spinner is 1 plus gamma 5 is equal to 1. No, it shouldn't be gamma 5 here, gamma 11. 1 plus gamma 11 is equal to 1. What is gamma 11? It's the product of all the spins.
Gamma 10s.
It's product of gamma 1, gamma 2, which is the spin in the 1, 2 plane, times gamma 3, gamma 4, which is the spin in the 3, 4 plane. So 1 plus gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, gamma 7, gamma 8, gamma 9, gamma 10 is equal to 1. It's simply the condition that S1 times S2 times S3 times S4 times S5 is equal to 1. Which means that an odd number of that only an even number of guys can be negative, and therefore an odd number have to be positive. Right? So chiral spinner is one where even number of guys is negative. Maybe that's how I should have said it. Where an anti-chiral spinner is one where an odd number of guys is negative. Okay? So your usual definition of chirality is the same as the condition that either even or odd number is positive or negative. Okay? So this guy is the chiral spinner. Whereas this guy is anti-chiral. And this guy is the chiral spinner. So another way of saying it is, if you take the zero mode sector for the fermions and decompose it into chiral and anti-chiral spinners, the chiral spinner part is the part with -1 to the f is +1. Whereas the anti-chiral spinner is the part with -1 to the power f is -1. Is this clear? Okay? So this ground state sector for the fermions has both -1 to the power f +1 and -1. Which one it is whether the spinner is chiral, whether we're looking at the chiral part or the anti-chiral part of the spinner. On the other hand, in the NS sector, the ground state unambiguously has -1 to the power f is -1. Okay, wonderful.
Just in terms of the degeneracy of the ground state, the Ramon sector has a much bigger degeneracy.
Yes.
And it's basically by all the possible ways you can arrange spin up, spin down for your H fields. And then the Nevertort sector is just one ground state.
Exactly right. Right. Perfect. Okay. So now what we're going to do is to allow ourselves to deal with either the Ramon sector or the Nebuchadnezzar sector, and also to deal with separately with -1 to the power f being either +1 or -1. Okay, so I'm going to use Polchinski's notation for this. He's going to use alpha comma f. F is -1 to the f. Okay, this tells you whether we're dealing with a sector where -1 to the power f is positive or negative. Okay, this guy alpha is 0 in the NS sector and 1 in the Ramon sector. Okay. Now, I am going to be interested in defining a well-defined theory on my world sheet. One of the conditions we've seen before for defining a well-defined theory is that all the vertex operators in my theory are mutually local with each other. What does that mean? It means that if I take one vertex operator, taking another one around it, circled around by 2 pi, I come back to myself. I want correlation functions in my theory not to be branched covers of my manifold, but to be functions of the manifold. Question of what the correlation function is when I put these things at certain points should be well defined. There should be no ambiguity whether I've taken it round or not. Okay, this is the condition we used before, right, when we discussed these Narayan lattices, and we'll use again.
Is this really a necessary condition, or is it just we're going to do it now?
No, it's necessary. Because, we want, well, I don't know, of course one can always generalize, but the way we think of quantum field theory, observables, we have correlation functions which are numbers associated. I put my operator here, 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 I get a number. It shouldn't be that I have to tell you not just where I put the operator, but how many times I took it around the other operator. The answer to a correlation function should be a number. Maybe you can generalize the structure of quantum field theory to go beyond that. But in quantum field theory, as we traditionally work it out, correlation functions are observables, which means that they are unambiguous. Okay? Now, I'm going to try to understand when this happens. Okay? So the question I'm going to ask is this. Okay. So let's start slow so that we build it up intuitively. First, just in the matter sector. Okay? Just in the matter sector, I'm going to ask, if I take an operator around another operator, okay? If I take an operator around another operator, what phase do I get? Okay. Now, so let's just work it out. Suppose I have e to the power I alpha a h a. No funny phases are going to come from anything but the exponentials. Right? It's going to come in that normal ordering of the exponential. So all the other del h's and so on will play no role. Okay. Suppose I have e to the power I alpha a h a. Okay, and I have e to the power I alpha a prime h a.
Didn't we do this again at the condition with? Didn't we run into this issue and then we said that generically you need the two, the right and left to match, and then we had the otherwise in the compactified version there was a different condition.
Yes. So we did it with one h, and we got a unique answer basically. Okay. Now we're going to have much more freedom because we have 5 h's, and we've got these coasts. Yeah. So we're just going to repeat that thing, but to do it a little more systematically. We'll see. You'll see. We'll have many conditions, many solutions. Okay. So suppose I take this at z, and I take this at 0. Okay, and I take this operator around that operator. Okay, so I take this at z and this at 0, and I take this operator around that operator. What do I get? Well, we've done this kind of calculation a zillion times before. But let's do it zillion plus 1. Okay, so HA with HA gives minus log z. Minus with minus makes it plus log z. Okay, and so we get z to the power alpha A prime sum over A. Did I call them essays? It doesn't matter. Alpha A's. Alpha A prime. So for instance, as a check, suppose alpha 1 was, in both operators, alpha 1 was non-zero, alpha 1 was 1, and the remaining alphas were 0. That would make this psi 1, and that behaves like Z, as it should, because psi 0 squared is 0. Okay, but if we did alpha 1 is 1, alpha 1 prime is minus 1, and the rest are zeros, that will make it 1 by Z, as it should, because psi bar was 1 by Z. This is just a generalization of that. Okay. Now we want to put in also the ghost part. Okay. So now we're going to just generalize this a little more. I'm going to do a slightly more general calculation. So suppose we take e to the power I alpha A H A, and I put in plus what, as we did before, A phi. And we do e to the power I alpha A prime H A plus A prime phi. Okay. So then we get Z to the power we get Z to the power sum over A alpha A prime plus A prime plus minus A prime. I hope, yeah, it won't matter. Because phi was minus log Z. Right, that minus got cancelled here because of the i's. I hope this minus is not going to cause trouble in the algebra I'm going to do now. I hope I've got all my conventions right. But okay, let's see how it goes. Now, therefore, the net phase that I pick up when I take 2 pi I is e to the power 2 pi I times alpha A A prime minus A prime. Let me check how Polchinski defines his fermion number. Just one. But it won't matter, right? What?
If you consider them to be a vector alpha, comma A,
Yes.
then its infinity linear product is the A sector.
Yes. Yeah, f is e to the power L phi. That's how he defines his fermion number. So sounds good. Let's go with this. Okay. Now I want to give you a rule. I want to show you that this object here actually only cares about whether the two operators were in the Ramond sector or Nebel-Schwarz sector, and whether they had plus or minus fermion number. Let us first take the case where both operators were in the NS sector. Okay? If both operators were in the NS sector, then every alpha is an integer. Every alpha prime is an integer. And A and A prime are both a particular integer, namely -1. Okay? So it's totally clear that this object is 1. Right? Which is basically the statement that psi's are mutually local with each other. Okay? The funny things are these spin fields. These guys in the Raman sector. Is this clear? What? E to the power minus 5? Why do I include it? Because I'm interested in the full operator. So the things I'm going to scatter will be in the ground state of the beta gamma system, and then whatever it is in the matter sector. Right? So I'm going to be interested in the full operators that will actually we'll be working with for scattering string gates. Is this clear? So in the NS sector, this phase is trivial if both operators are in the NS sector. Okay? It doesn't matter what the fermion number was. NS times NS, if we have NS plus minus times NS plus minus, independent plus minuses, phase is equal to 1. Clear? Everything interesting is going to require a Raman. Okay? Now, let us first now do Raman, let's say plus with NS. Let's do Raman with NS. Okay? We've got many choices. So just to be totally concrete, I'll do one choice first, and then we'll see how it generalizes very fast. So let's suppose we do NS plus Raman plus with NS plus. Okay, so suppose the alphas were in the Raman sector. Okay, and so suppose the alphas were in the Raman sector, and the alpha primes. So first I'll do this part, then we'll deal with this part. So suppose the alphas were in the Raman sector, and the alpha primes were in the. Oh, so actually let's do this part first. This is the easiest part. This part is
A is in the Raman sector.
A is in the Raman sector, so that was half, no, minus half. And A prime was in the NS sector, so it was minus 1. So the product is minus half. Okay? So in this case we get e to the power 2 pi I times alpha A prime minus half. Okay? Now let us suppose we have I'm going to start with an example. So this was all pluses. So one example is all of these were plus half, plus half, plus half, plus half, plus half. The 5 plus halves as we saw at the beginning. Okay, so one example is half, 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 half. Now we want NS plus. You see, because of this factor, the vacuum is in the minus. So the simplest NS plus state is one psi turned on. Is this clear? The NS vacuum is fermion number minus.
NS vacuum was C times e to the minus.
And C had nothing to do with fermion.
C nothing to do, C to the minus pi was the vacuum.
Vacuum.
And this plus means the fermion number plus.
Yes.
So the vacuum has fermion number 1.
Fermion number minus 1, yeah.
Fermion number minus 1 probably.
Minus 1. Okay. So if we want an NS plus state, the simplest state would be one psi.
Yes.
Let's say that we had 1, 0, 0, 0, 0. Okay? So in this case, what are we going to get? We're going to get 1 into half minus half. So this once again will give us 0. Now I want to make it. It should. What we want to understand is that this was not a feature of this example, this choice of states, but only about which sector we're in. Let us first see.
In other words, R plus and NS plus always a fermion number plus 1.
Always a fermion number plus 1, but yeah. But let's see how this goes. You see, suppose I looked at a more complicated NS sector state, but also always with this Ramon sector state to start with. Now, because the NS sector state has to have fermion number plus 1, what I want, see, I showed you that I took an example of a particular Ramon sector state which had positive fermion number, and a particular NS sector state which had positive fermion number. And I showed you that the mutual phase for this particular choice of states was plus 1. Now I want to try to convince you that that answer is true of every state, every pair of states in the R plus and NS plus sector, and was not just a feature of this particular example I chose. Is this clear? The first thing I'm going to do is to first stick to this Ramon sector state and generalize the NS sector state. Now, how do I generalize the NS sector state? I add or subtract integers from here. Because in the NS sector, these guys are always integers. But because I want to stay NS sector plus
1. So there can be odd number of plus 1.
I have to have, exactly. I can, compared to this state, I can only add an even number, change an even number of integers.
Yes.
Even number of integers, or have to change an integer by an even number?
Right. So more precisely, the sum of these 5 integers can only change by an even amount.
So if I just change the first one to be 3.
Suppose I just change the first one to be 3. That doesn't change this, because you see, that is the additional factor is 2 into half, which is an integer. More generally, with this Ramon sector state, what I get is the sum of the integers from here, because all the halves were the same.
That should not change. So
Yeah,
that
the inner product should change by an integer. This alpha prime.
It's always going to be the sum of the
Yes.
integers times the half.
Times the half.
Exactly.
And then that's
And since the change in the sum of the integers is even,
Yeah.
it does not change.
And then there's only going to be the last half from the AA prime, which just.
Wait,
Yeah, that's
I'm just looking at the change in phase because I've changed the NS sector.
Yeah, no, I think what you were saying was with the EA prime always remains minus half, and so
Yeah.
the R plus NS plus always is.
Yeah. The way I'm thinking is, in one example of this state, I get phase 1.
Yeah.
Now I'm going to change the state and see what the change in the phase is.
Yeah.
So I don't have to worry about what we've already done.
Yeah.
And the change here, if I change the NS sector state, will always be by an even integer, by an integer.
By an integer.
So it'll always be by 2 pi I times an integer.
Yeah.
So that doesn't change it. Okay. Now, what about when I change this guy?
That also has to change by an integer.
Now what about when I change this guy? Exactly. Exactly. All of these, that is almost trivial.
Yeah, plus half to minus half.
Exactly. Although these values are half integral, the changes are always integral. So the change will always hit something here, which is always an integer.
Yeah. And the two of them have to be changed simultaneously to keep it in R plus.
R plus, but we didn't even need that.
Yeah, okay, right. Yeah.
Right?
Yes.
Okay? And therefore, the changes in either this state or in this state don't affect it.
Yeah.
This is only a property of which sector we are in. And so we've concluded that the phase between R plus NS plus and, R plus and NS plus is plus 1. Okay. Now we need to go through such an analysis for each of the sectors. I'm first going to give you the answer, and we'll test sample sectors. And I'll leave the rest of the testing for you as an exercise. Okay. Now we'll use Polchinski's notation. I pi by 4.
I'm making some random thing, but I just want to understand the relation.
Well,
It looks like the rotations in the size are the symmetry in H's.
see, firstly, if my thing was I pi by, say again, Fermion number is what? I alpha by 4, you're saying. I sum over alpha by 4. Then, you know, Fermion number firstly won't have only 2 values, plus 1 or minus 1.
That will not have.
Yeah.
It will have
Many things.
4 sectors.
Yes.
I am saying that it is fine that you will not have 2 sectors, you will have 4 sectors.
Yes. Yes.
And then still this argument will go through or not? This mutual localities argument?
No, I mean, it will depend, I mean, sector by sector. Wait, firstly, I'm not even sure if it will depend only on the sector.
Yes.
I'm not even sure of that.
So something very correlated is happening.
Yeah, you know, basically what's happening is this. Look at the actual formula, and then you will see. Basically what we are saying is that fermions pick up either a square root z or a 1 by square root z when they go around the Raman sector. Okay? And whether they pick up square root z or 1 by square root z depends on whether they're psi or psi bar.
So you are saying that because Raman sector has half integers,
Exactly.
that is related to this I pi.
Yeah, you see the Raman sector has this twist operator. The twist operator has this square root z singularity.
Yes, that is the half.
That is the, now the danger is that you want all the square root z's to cancel in the end.
Yes.
Okay? So the question of whether you get square root z or 1 by square root z is the minus 1 to the f.
Yes, therefore you need to define it to be I pi, multiplied with I pi, because it is like.
It's mod z2, right?
Yes.
Square root z times square root z is 1.
Yes.
Okay, that's basically what's going on. Okay, now let me write down Polchinski's formula. Polchinski has a beautiful general formula, which also is quite intuitive, makes this intuition a bit clear. He claims that the answer is always exponential of exponential y pi alpha 1 f2. He does it the other way around, but it makes no difference, I think. But okay, let's write it our way. Let's write it his way. I've learned from experience that you stick to Polchinski. If so, you think, oh, it does make a difference, and then later on you see, that's why he did that. Okay. Okay. So fine. So you remember what alpha was? Alpha was a number that was 0 in the NS sector and 1 in the Raman sector. Minus 1 to the f was 1. Yeah, let me actually wait. Now, is it minus 1 to the f or not? Sorry, this may be serious. I think he does f. Sorry.
Yeah.
F. Notice that if f increases by 2, it will not change this object because it will change this thing by an even integer because alpha is either 0 or 1. So f is only defined mod 2 for the purpose. So let's deal with f, not minus 1. Okay. So in the NS sector, so what have we checked so far? Firstly, anything where both these guys are NS sector, this is always phase 1. That's clear because in this case both alpha 1 and alpha 2 are 0. So that's phase 1. Okay. The other thing we've checked is that if we take R plus, so plus is f equals 0.
Yes. So that is also.
Yes. So suppose f1 was 0 and alpha 2 was 0. That also, sorry.
R plus will also work.
Well, let's check R plus NS plus. So,
Don't table.
yeah, yeah, that's right. We should. But let's see. So suppose we've got R plus. So plus means F2. No, let's call this guy 1 and this guy 2. So F1 is 0. So we can forget about this term.
Alpha 1 is 0.
And now, no.
Sorry, alpha 1 was
Alpha 2 is 0.
But F2 is 0 because we've got both pluses. Yeah. Yeah.
Yeah.
Right? Both pluses, so F1 and F2 are both 0, so you get 0, and that also gives us phase 1. Just to make sure that we trust Polchinski, let's work out a case where we'll get phase -1. Okay? So let us take the following case. Let us take a case where, let's say that alpha 2, let's say that alpha 1 is n sector. So this will go away. But alpha 2 is Ramon sector and F1 is minus. Okay? So that will be a phase of -1. Okay? So let's check that case. So Polchinski's prediction.
example, it is symmetric between left and right index.
Yes.
Because if you flip, you get a minus I pi, which is a 2 pi I times this,
Yes.
which will be always 1.
This thing is always either 1 or -1.
Yes.
So whether it's e to the power I pi or e to the power minus I pi, it's the same.
Yes.
The minus sign makes no difference.
So left and right, you don't have to worry separately.
Yes. It's just the statement.
Yeah.
This picks up a phase, then that also picks up a phase. It's just property of the 2-point function. Yeah. Okay. So Polchinski's prediction is that if we start in the NS minus sector, that was the F1 equals 1, and then we take the R and anything,
Yeah.
plus or minus, okay, R plus or minus, we should get -1. Right? Because alpha 1,
Is 0 because of.
wait, I mean,
NS.
wait, no, sorry, NS sector, so alpha 2 is 0.
No, I mean that one is 1 over there, right? I mean what you have written.
This was 1, exactly. So because it was an NS, number 2 was the NS.
Yeah, I mean no, over here.
Okay, sorry. Okay, let's do it the way we've done it here. So say this guy is 1 and this guy is 2.
Yeah.
Just to check again.
Alpha
So
1 is 0.
alpha 1 is 0. So F2 could be anything.
Yes.
But alpha 2 is 1.
Yes.
As long as F1 is minus, we should have trouble.
Yeah.
Let's check this prediction. Okay. So for the let's work it out carefully. Let's check a state in the Ramon sector. Okay. So let's start with R plus and then we'll also see the reverse Fermions. So let's suppose we have half, 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 half. Now, once again, this minus AA is a factor of -1/2.
You already have 5 there.
What?
You already have 5 over there.
No.
Count them to your 8, right?
What?
In that vacuum growth, you have 5.
I have 5, and then this is the ghosts.
The alphas, there's 4 of the alphas,
No, 5 alphas.
5 alphas. Okay.
Because we're doing the covariant calculation. So number of fermions is 10.
Yeah.
So number of bosons is 5. Plus ghosts. Okay. So I'll write down the thing we're considering. And let's suppose we take the vacuum.
That's already minus.
Yeah. 0, 0, 0, 0, 0. Okay. Now, let's look at what was the sum we had. We had e to the power alpha.
Minus I pi.
Exactly. Alpha e to the power I pi, alpha a, alpha alpha prime A minus AA prime. That minus AA prime was minus half.
So I think that was 2 pi I.
That was 2 pi. Thank you. Thank you. 2 pi. Was minus half. Now, we've chosen one of the alphas just to be all zeros. So these guys go away, but there's a minus half from here. Okay? Notice that if we'd chosen a minus here to put the Ramon in the other sector, it would have made no difference. So R plus minus, as long as you're with NS minus, gives you trouble. Is this clear? Oh, it gives you a phase of -1. Okay? And you can go through the same arguments we went through to convince yourself that it doesn't matter that we chose this particular example. It only depends on the sectors. Same kind of arguments. Okay? Good. So,
this implies that any NS minus and R plus minus does not give a consistent stream.
a mutually local phase. Wait, but so far we've worked with left movers.
Okay.
We have to put in the right movers.
Okay.
At the moment, we've just made a conclusion about what phase you get. Is this clear? Okay. Now, clearly, if this is true,
Just like sort of a conceptual question.
please.
Suppose number 2 was, suppose all I was looking at was the first term, the alpha 2 F1. In other words, that I had, that would mean I would have the Ramon would be 2, and then 1 would be number shorts.
Good.
Right? So then this is telling me that all I care about is the parity of the Nebula shorts, of the number of fermions in the Nebula shorts. I don't care how many fermions are in the Ramon sector.
Yes.
Right?
Yes.
But the Ramon sector seems like the place where the minus halves would show. The balancing of the minus halves seems like should happen in the Ramon sector.
Yeah. Why? How come that? It's this way. See, suppose you've got a Ramon sector state, then one fermion going around it picks up a square root z.
Yeah.
But two fermions going around it pick up square root z times square root z, and therefore integer. So the Ramon sector state is the thing that could cause trouble. But it's clear that that trouble goes away in bilinears. If the other guy is in the NS sector, and you move it in bilinears, the trouble goes away because it was square root z. So you see that whether or not there's trouble can only care about number of fermions modulo 2
But that's the number of fermions in the other sector.
in the other sector.
Right?
Yes. So that's what we found, right? We found that alpha was non-zero because 2 was the Ramon sector.
Yeah.
And then whether there was a trouble or not cared about number of fermions in the other sector. F1 for the other operator. So you need both to have trouble. You need a Ramon sector in the game, and you need the wrong number of fermions going around. Well, that's what this formula is saying. It's a very intuitive formula if you think about it. Right? That for every Ramond sector, you get a bad phase because of wrong number of fermions. Okay? So I'm going to leave it as an exercise for you guys to check more seriously. This formula, check one Ramond
So this
sector.
is the only case which does cause trouble, right?
Well, no, we could have trouble in the Ramond sector.
Ramon plus with Ramon minus would presumably cause a problem.
Exactly. See, suppose, exactly. Suppose we had both Ramond sectors, then both alphas would be +1.
Yeah.
So this would be F1 minus F2.
Yeah.
Now, if one of the Fs was
1 and 1, the other was 0.
one of the Fs was 1 and the other one was 0, you'd have trouble. Right? So this is the general formula, and you can test it in. Would you like to check one Ramond sector, or are you happy? No, everyone's happy. This is only about the left moving. That's a crucial comment. Now, the actual theory has both left moving part and right moving part. Okay. The actual theory is both left moving part and right moving part. And so clearly what we're going to get is that the net phase is going to be exponential of I pi alpha 2 f1 minus alpha 1 f2. And then if I wanted to be a purist, I would write in the other one. But it makes no difference because it's always plus or minus 1. So I'll just write plus alpha 2 tilde f1 tilde minus alpha 1 tilde f2 tilde. You know, some of you are thinking, look, z bar picks up the opposite sign phase from z. So shouldn't that come with a relative minus sign?
Yeah, but overall minus.
Yeah, it makes no difference. I'm just writing. Yeah. It's correct. It's a correct worry, but in this case it makes no difference. Okay, you could for the same reason that you could flip these around, right? Okay, but let me see how. Yeah, even Pulchinski has written. No, never. He's written in the. Yeah, he's written in the elegant way. Okay, not that makes a difference. No, this is. Okay, so this is the net phase. And now the real statement is that we're going to have to choose something on the left and something on the right. And our choices will have to be, so the whole thing is mutually local. So what's the game? The game is suppose I make a choice of projection, which is I'll give you a list of sectors. This on the left, this on the right, plus this on the left, this on the right, plus so on. I want to classify the full set of mutually local sectors. That is my goal. A full set of possibilities. Okay? Very good. Now, mutual locality is only one ingredient. Okay? The other ingredient, as we saw in one of our classes, is going to be modular invariance. Modular invariance implies the mutual locality, but is a little stronger. And there's one element of modular invariance that I'm going to put in this discussion. We'll study modular invariance in its own right in great detail afterwards. But for this discussion, I'm going to put in one element of modular invariance, which is this. There has to be at least one left-moving Ramond set, every modular invariant partition function. Basically what I'm saying is that it's impossible to build a modular invariant partition function. Okay? It's impossible to build a modular invariant partition function without having at least one left-moving Ramond sector and having at least one right-moving Ramond sector. The reason for that we've already been through. Let me remind you. Suppose on the left, okay, whether it's Ramond or not, Ramond is plus here. Okay. Suppose I try to build a modular invariant with only minuses here. In order to be a modular invariant under S duality, it has to have a minus here. But then if we look on this cycle, it's plus. So then it's not modular invariant because
Now S transformation
we'll break it. Right? So it's an obvious statement that it's impossible to build, while it might be possible to build a modular invariant without NS sectors. Yeah. Yes. It's obvious you cannot do it without Ramond sectors, without the pluses. Okay? So we'll study modular invariance in much more detail in a bit.
minus sector what? And anti-periodic.
Minus sector was
Raman sector. Minus was Raman.
here
This
it's
one is NS.
minus is NS. You see, we're working on the cylinder.
Yeah. Now it's
What's
space
the cylinder?
Cylinder or torus. So when we quantize on a circle,
Yes. So,
antiperiodic is never Schwarz?
in a sector. then.
Yes, yes. So we need at least one plus. If we try to get away with only minuses, I've made a contradiction.
What if we stayed on the cylinder and never went to the torus and never worried about this looping
You know, as you might remember, our formula for string scattering amplitudes involved computing things on higher genus surfaces, including the torus. Nothing will not be well defined unless it's modular invariant.
For example, some vacuum loop diagram could involve simply just tori, right?
Yeah, exactly.
Yeah,
A one
I
loop
mean,
diagram,
yeah,
finite temperature free energy will involve that. One loop scattering amplitudes will involve it.
Yeah,
But the important thing is that this modular invariance came just from large diffeomorphisms on the string world sheet. You know, some diffeomorphism will convert this cycle to that cycle. Okay? So if it was not modular invariant, it meant that our whole starting point would have to be rethought, because diffeomorphism was one of our sacred principles.
No, but then why do we think only about the torus and not about higher genus?
That's because, you see, once you have modular invariance on the torus and one or two small conditions, modular, you know, the analog of modular invariance on the high genus surfaces is basically automatic.
So
Okay.
we can sew together different tori, right?
Exactly. This is the general conformal field theory result. That, you know, if you have the OP, you know, crossing symmetric OPs on the plane, plus modular invariance, plus one more thing, modular invariance also including one-point functions on the torus. There's a general proof that all the good properties of higher genus surfaces work out automatically. That's why modular invariance is sort of a key. On the torus, modular is a key.
You always need a Raman sector. That was the purpose.
Yeah, we need at least one Raman sector. At least one left-moving Raman sector, at least one right-moving Raman.
I mean, this is probably a stupid idea.
Go on, go on.
Suppose you had something without modular invariance, would you then be able to say, okay, then everything has to happen at tree level?
Oh, so you want to define a classical theory of gravity rather than a quantum theory of gravity.
Right, and then you
Okay, but you know, that's greatly lowering the ambition of string theory. We wanted to do, yeah. I suspect even there you'll have trouble, frankly. There's something Indranil and I are working on, that classical scattering in gravity is much more constrained than you might think. For instance, classical gravitational theories easily violate causality constraints in ways that are non-obvious. In string theory, it doesn't happen, but it doesn't happen once you do everything right. I suspect you could try. I suspect you'll run into trouble. Okay. If your goal was just to define good classical theories of gravity, maybe you could give up some of these principles, but I suspect that even classically, it will come back and hit you. That's my suspicion. Okay. So fantastic. So we've concluded that there must be at least one left-moving Raman sector and one right-moving Raman sector, otherwise modular invariance is impossible. Okay? So now what we're going to try to do is to build up all possible mutually local sets of sectors with this condition. There's one last thing I have to tell you before we start building, which is this. Let us remember the level matching condition. The level matching condition was that L0 was something, either 0 or 1, depending on whether you take into account the ghost contributions or not. Okay? And L0 bar was the same thing. Okay? Let's.
One identity for 2 pi rotation on the cylinder.
Right. That was an. But actually, just physical state condition. That L0 is whatever it is. That came from T is equal to Ta annihilates this, our states. And L0 bar is whatever it is. Now, since they're both whatever they are, they're equal to each other.
The statement that they are equal to each other was the statement that rotation by 2 pi was trivial.
Yes, you can interpret it that way. But I'm saying you needn't. L0 was 0, L0 bar was 0, therefore L0 is L0 bar. Because 0 is 0. I mean, okay, it's true. But okay, now that tells you that L0 is equal to L0 bar. It's true what you say. Okay. Now, remember what L0 and L0 bar were. There was a p squared alpha prime p squared by 4 contribution, plus there was n oscillator. This was on the left. And similarly, there was a similar contribution on the right. Well, if we wanted to, if we were working on the cylinder, there would be a central charge term. But I'm talking about L0 on the plane at the moment. Right, I just want to put the condition that the state was a 1-1 primary. Okay, so I'm just writing down the dimension of the state. Okay, so alpha prime p squared by 4 plus n oscillator right. Okay, so at a given value of p squared, this tells you that once I know the left moving oscillators, I know the level of the right moving oscillators. This is that's why it's called level matching condition. If I give you what the oscillator number is on the left, I already know it on the right because the p squares cancel. Now, however, look at this. Suppose we are in the NS minus sector. Okay? In the NS sector, every fermion is half integrally moded. And in the NS minus sector, okay, now I'm going to say it first wrong and then I'll say it right. Saying it, I'll say it wrong because I'll ignore the ghosts. What I'm saying now would be correct in light cone gauge. Let me say it in light cone gauge and then I'll say it right because the ghosts are a pain in the neck. But okay, let me imagine I was saying this in light cone gauge. Okay, then I'll say it correctly. So in the NS minus sector in light cone gauge, there are no ghosts. Okay. Whether that n oscillator was integer or half integer would be a question of whether there was even or odd number of oscillator modes, because every oscillator is an integer. Okay, so you act with an even number of modes, you get an integer. Odd number of modes, you get an half integer. On the other hand, suppose we were in the Raman sector. Okay, all the oscillators are integers. So if you are in the NS minus sector, minus meaning odd number of, if you are in the NS sector and you have an odd number of fermionic oscillators, your level is at half integer. That could. Yes.
First, this depending on if it is half integer or integer, this your n oscillator sum will have half integer or integer.
Correct. You see, because n oscillator is just contribution from each oscillator.
Yes.
Now, every oscillator in the NS sector is half integer moded.
Yes.
Okay. So if I have one photon of an oscillator, it's a half integer. N oscillator is necessarily a half integer. If I have 2 photons of that, it's necessarily an integer.
Yes.
3 photons, half integer, 4 photons.
Yes.
So depending on whether I have an odd number of photons, an even number of photons, I have either half integer or integer.
Yes.
On the other hand, in the Raman sector, all oscillator numbers are integers.
Always integer.
Okay. So if you want level matching, so if on the left you've got the NS minus sector, and on the right you've got any Raman sector, level matching is impossible.
Yes.
Okay. Moreover, if you have NS minus on the left and NS plus on the right,
Then also you can.
level matching is also impossible.
Yes.
Okay. So the conclusion, and then I'll say it better. I'll say it more with the ghosts.
And when you concluded this, first you ignore the ghosts and you ignore the C's also.
C's have nothing to. There's
Wait,
C's are always integer moded.
C got cancelled out because of matter and ghost cancelled.
But also every C oscillator was integer moded. C and B oscillators are always integer moded. it's only the fermions and the beta gamma that could have half integer motive.
I said central. You are doing the calculation on the cylinder
Yeah, firstly central charge will be 0
because of this cancellation.
because of cancellation. Firstly central charge is 0. Secondly I'm looking, yeah, okay, central charge is 0. So let's just say that.
Because of cancellation.
Yes.
And you ignore the ghosts.
Yes.
And you did the calculation on the cylinder. It probably will not matter. You do it in the
Well, I actually didn't do it on the cylinder. Well, you could say it on the cylinder, but I was actually doing it for the operator dimensions.
Yes.
So I
It
will.
will not matter. Okay. You need to take into account ghosts.
I need to take into account ghosts. Okay, but I'm going to write down the conclusion and then we'll derive it using the ghosts. So the conclusion is that NS minus cannot pair with R plus minus or NS.
This example also like this.
Yeah, it could be that some of these are also ruled out by phases, but independently, for instance, NS minus NS plus is not ruled out by phases. Because when we had both NSs, the phase was +1.
Yeah.
Also, the phases could, yeah, right. Sorry, I should also say that we're mixing up things. You see, when I say pair with, I don't mean mutual locality. I mean on the left and on the right.
In one theory,
Eh.
holomorphic and in anti-holomorphic.
Yeah.
I'm sorry.
Yeah. So then about mutual locality, will have to give me both pairs on the other side and then look at that.
It is totally different.
So it's a different thing. Yeah. Okay. Excellent. So now let's take into account the ghosts.
But suppose I had NS minus on the right and NS minus on the left.
NS minus on the right and NS minus on the left, that would be okay. That at least this condition would not prevent you from doing it. There may be some other problem, but this will not stop it. Okay, so now we want to take into account the ghosts, and in order to do that, we need to take a deep breath and proceed. Okay, fine. So let us see. Firstly, if we want to do this with ghosts, what we want to do is to match scaling dimensions. L0 is a scaling dimension. L0 bar is a scaling dimension. So that's what we want to do. So let's see. So now we have to take into account lots of scaling dimensions. Okay. So what was the scaling dimension of e to the power minus phi? Upmanyu, would you mind? 5 by 8?
To the power minus phi was minus lambda prime minus 1 and lambda prime was equal to
Sorry, I'll get it quickly. Half?
divide if lambda prime is equal to
Yeah, I'll just check this here. I got h is equal to 3 by 8 here. Remember, this is the phi with the ghosts.
yeah, minus phi is a half. Your lambda
Minus phi was, I'm sorry, you're right. This was equal to half, and e to the power minus phi by 2, sorry. Was equal to 3 by 8. 3 by 8.
Yeah.
Okay. Now, let us also add in, if we want, C. Okay. So that makes this minus half. C, that makes it minus 1. The C will play no role. So it doesn't matter, but let's put it in anyway, because just for logic. And in the ground state on the Nebel-Schwarz sector, in the ground state, that's it. But in the ground state in the Raman sector, that's not it. because we have e to the power I SAHA. Okay. Now, e to the power I HA, remember in this normalization it was k square by 2. K squared is half. So each of those e to the power I SAHAs has dimension 1/8. So this whole thing has dimension 5/8. Okay. So plus 5/8. Yeah. So this guy is 0, whereas this guy is minus half. Now, therefore, the sector that's going to have trouble will have an even number of matter fermion oscillators. But even number of matter fermion oscillators is ns minus sector, because the ghost vacuum has fermion number -1. Okay? So you see that the Raman sector always has n oscillator. I mean, always has L0 is equal to an integer, L0 after taking out the p square by 4. The Nevu-Schwarz sector has L0 is equal to an integer in the ns plus sector, because an odd number of matter fermion oscillators puts you in the ns plus sector, whereas an even number of fermion oscillators puts you in the ns minus sector. So the conclusion follows.
You want to extend ns plus with ns minus?
No, ns minus. Ns minus is even number of fermion oscillators.
Ns minus is even number of fermion oscillators, and that is still half.
Yes, that is the thing that has trouble. We got it from different sources, but it's still the same conclusion. It's just that you could have done the calculation in light cone gauge, so the first thing was not wrong. It was a correct argument, just in a different gauge.
But the previous argument, unless I misunderstood the claim,
Yes.
didn't get me to the argument that concluded it. The previous argument had me fine with ns minus, ns minus.
Yes, same here.
And I thought we were going to say that you have to have at least one left R and one right R.
Yeah, that's a separate statement. Okay, we've made many claims. One is that ns minus cannot pair with any of the other sectors, can only pair with itself. If you have ns minus on the left, you have to have ns minus on the right. The other claim is that both in the left moving sector and in the right moving sector, you have to have at least one Raman sector. Okay, both these are true statements, they are independent true statements.
Only thing
And,
that's in
and the mutual locality consists only one side, either the left moving side or the right moving side.
What do you mean?
The mutual locality, the two operators that we are considering in mutual locality,
Yes.
they were in the same side. I mean, they were.
No, but now we added the phases. You see,
Yeah, I mean, okay, right. Oh yeah, over here, obviously, they both have.
mutual locality is a property of which sector and -1 you are on the left and on the right,
Yeah, yeah.
and the other operator
Yeah, the two of them taken together.
together. So complete specification of the sector in left and right for the first operator, complete specification of the sector left and right, second operator. Okay? I can't hear you. Both the statements imply that? No, nobody is saying ns minus cannot occur. But if it occurs, it has to occur with ns minus on the other side. About mutual locality, that's another matter, which we'll have to understand.
modular invariance with one left R and one left.
Yeah, see, it cannot be that only ns minus occurs. See, if you look at all allowed sectors in your theory, one of the allowed sectors has to have a Raman part on the left. There's no claim that every allowed sector has that. Do you understand? Okay? Now we're going to proceed. Now we have all the information we need to proceed. Okay. Okay, so let's go. Okay, fine. We know that there is, okay, we know that there must be at least one R sector
Each side.
on each side. So let us first assume, okay, this I'm clearing. This is clear? Actually, quite clear. Let me assume that there is, so there are two cases. Since there's at least one R sector on the left, there has to be either an RNS sector, meaning left is R, right is NS, or there has to be an RR sector, or both. Okay? So I'm going to take two cases. First, that there exists an RNS sector. Second, that there does not, in which case there must exist an RR sector. Okay? If there exists an RNS sector, there may also exist RR sectors. That's fine. But so I'm going to assume that there exists an RNS sector. Say such a sector exists. Now, since this sector exists and level matching works, this sector has to be NS plus. Because if it was NS minus, it couldn't pair with anything except NS minus. Okay? So we have two options under this assumption. So we've made the assumption. And then we have to take, under this assumption, there are two options. Okay, the two options are that we either have an R plus, NS plus, or we have an R minus, NS minus. We may have both, but at least one of these two must appear. Sorry, not plus, minus. Plus. Okay. Now, first question we are going to ask is, can both of these occur? This is now an issue of local mutual locality. Okay, so I'm going to take the relative phase between this guy and this guy. Okay, and see what we get. So the relative phase from the right movers is 0.
R plus R minus cannot occur together.
Cannot occur together.
Cannot occur.
Cannot occur. It's a relative phase from the right movers is 0. And precisely in answer to Upmanyu's question about whether the Ramond sectors could have a problem in mutual locality. So all of the phases from the left moving side. And remember that this was basically e to the power I alpha 1 f2 minus alpha 2 f1. In this case, alpha 1 and alpha 2 are both 1. So it's e to the power I times f1 minus f2. But f1 minus f2 is also 1 because one of them is plus and the other one is minus. Okay, so they can't both occur. So this guy is either or. Okay. Now there must also be
NS plus.
okay, good. See, there must also be an NSR or an RR sector.
Yeah.
Because on the right also there has to be at least one R sector. Now look, suppose the sector was an RR sector, not an NSR sector.
Level matching would be.
Look, that will may or may not be, but now let's take the OP of this RR sector with either of these cases.
Okay.
Now the rule is that Ramond with Ramond gives Neveu-Schwarz. Think e to the power IH by 2 times e to the power h by 2 gives e to the power h. Half integer plus half integer gives integer. Okay? So suppose there was an RR sector. Doing the OP of that with either of these cases would give an NSR sector. Okay? We know that one of these two sectors has to exist, but if this sector exists by OP, this must also exist. So in either case, the NSR sector must exist. Okay?
If you have RR sector, then you are doing OP between R and this R, which is
NS.
R and R is NS.
And NS and R is R.
NS and R is R.
And therefore you get NSR. Is this clear?
So you're saying if I had this and additionally I had an RR sector, I would get an NSR sector.
I mean, if we have
Exactly.
RR to begin with, then we must have NSR
Yeah.
sector.
See, we know that there is at least one R sector on the right.
Yeah.
That R sector could have been RR or could have been NSR. Suppose it had been RR. Then take the OPE of the RR with this RNS. That anyway gives you an NSR. So from either case, we know that there is an NSR. Okay? So once again we find, but now this is symmetrical. So again there has to be an NS plus R plus or NS
NS plus R.
plus R minus. In either case, one of these and one of these. Okay, great. Fine. So let's summarize what we have. So we've found that there are 4 possibilities at the moment. R plus NS plus and NS plus R plus, R plus NS minus NS plus and NS plus R minus. Okay, R plus R minus NS plus and NS plus R plus, R minus NS plus and NS plus R minus. So the full content, we've completely characterized the possibilities in which one sector is R and the other sector is NS. Okay? The paths where one sector is R and the other sector is NS cannot have anything more than this. Okay. Now, first question, are these sectors all mutually local? Are all these choices consistent?
Each one should be mutually local with the other choice.
No, just this is case 1, case 2, case 3, case 4. In case 1, this has to be mutually local with this. Case 2, this has to be
Between 3 and 4 and the second part.
between this and this.
3 and 4.
No, 3 and 4, it's never simultaneous. It's either this or this or this or this. The mutual locality only has to be tested between this guy and this guy, this guy and this guy.
Then let's check it in 3.
Let's check it in 3. Okay. So,
I think R minus
They're all supposed to work.
Okay.
Yeah. Okay. Let's see. So suppose we do first the left part. Okay. So it's alpha 1 f2 minus alpha 2 f1. Suppose this guy is 1. Since alpha 2 is 0, we can forget about this. Now f2 is 0, so this is gone.
Yes.
Okay.
Yeah.
Now do the right part. Okay. Alpha 1 f2 minus alpha 2 f1. Since alpha 1 is 0, we can forget about this.
And f1 is.
And f1 is 0, so we can forget about this. Okay. All 4 work is the claim, and you can sit and check them. Okay.
Is it because the NS sector is always plus? So you're essentially
I think you're right. I think you're right. I think you're right.
Yeah,
I think you're right.
The only thing that didn't work was ns minus with r plus minus.
Yeah, yeah, I think you're right. I think you're right. You see, but because every term has either an alpha or an f from here. But both alpha and f are 0. So everything's just going to be 0. Basically trivial. Yeah, well said, yes. Okay, excellent. Now, this can't be it because of closure of the OP.
One of these should be definitely there.
What?
One of these should
One of these has to be there. But now let's take case 1, for instance. Can this be all that's there? No, it can't because of the OP. Okay, suppose I do the OP on this guy with itself. What do I get?
ns.
NS plus, NS plus.
Yes.
Right? So certain, any sector with itself
Yes.
gives NS plus, NS plus.
Yes.
Okay? So NS plus always occurs. Okay, so clearly all of these will also have NS plus, NS plus. But how does this close? Let's see. NS plus with anything is itself. In this OP, in the sector-wise OP, it's NS plus is like identity.
Anything is itself. I mean the other thing, right?
We'll give you the other thing.
Yeah.
It's like the identity element.
Yeah.
So nothing interesting happens there. This guy with itself and this guy with itself both give NS plus. So what's left? It's to check this guy with this.
Yeah.
Okay?
That will give ns plus and no, that will give r plus.
R plus, R plus. And we get R plus, R plus. Okay? Now, anything else? Well, this guy with this is trivial. What about this guy with this guy? That gives NS plus, R plus, which is already there. What about that guy with this guy? That gives NS plus, R plus, NS plus, which is already there. So it's a closed OPs. Okay? And because every factor here has an NS plus, mutual locality between any one of these three and anything else is trivial. Since everything is mutually local with itself, mutual locality works. Okay? Great.
I'm a little confused about the original statement. Does that statement say that that both, at least one or both of the left and right must contain the R sector? Does that mean this NS plus, I mean, since there's an and between everything, so we cannot exclude this NS plus.
Yeah, NS plus must always be there from closure of the operator product expansion. If you have any sector, you'll always get NS plus.
Yeah, but does this entail anything unwanted for modular invariance? The presence of this NS plus.
No. Let's be clear.
Yeah.
Modular invariance means that it tells you that there must one of the options in the AND should have a left moving R, at least, and one of the options in the AND must have a right moving R. It doesn't say that everything has.
Yeah, that's what I wanted. Thank you.
Okay. Okay, now let's close this guy. Of course, we'll get and ns plus ns plus. I'll put that for everyone. Okay, but everything interesting comes from here and here. Okay, so here we get an r plus r minus. And you can easily check that this also closes this guy with this guy, for instance, gives ns plus r minus. Okay, here we will get an r minus plus r minus r plus. And here we will get an r minus r minus. Is this clear? Okay, and this combination of sectors satisfies every consistency condition we can think of, and as far as we know today is completely consistent. Now, you see, it looks like there's 4 cases, but actually there's only 2 cases. Because whether you've got r plus and r minus,
And R minus R plus.
you see, what's really important, in the Ramond, in the Nebu-Schwartz sector, plus and minus had a very physical meaning. Because the vacuum, the ground state, was either projected in or projected out in plus and minus. In the Ramond sectors, plus and minus just told you whether the vacuum was chiral or antichiral. Now, if you've got a chiral thing on the left side and chiral thing on the right, that's different from chiral on left and antichiral on right. But chiral on left is not different from antichiral. This is just a parity transform. Okay? So, you see, the only differences here are this.
The 2, 3 and equivalent. And 1, 4 at same.
Yeah. Here and this are the same under a chirality flip in the Ramond sector. Here and this are the same under chirality flip in the Ramond sector. But these 2 pairs are genuinely different from these 2 pairs. Okay? 1 and 4 has the property that you have the same chirality on left and right in Ramond sector. Whereas 2 and 3 have the property that you have different chiralities. 1 and 4 are called type 2b theory. Whereas 2 and 3 are called type 2a theory. You can see immediately that 2b theory is a chiral theory. Whereas 2a theory is not a chiral theory.
Yes.
Okay? Great. Good, we've done good, but we're not through because of you. Please.
So one of these four possibilities should be there.
We are listing all possible consistent subsectors.
Yes.
Okay? And we will find, there's one more thing we have to check. The thing we have to check is that we get a modular invariant partition function. But we will find it will work. Okay? So, not has to be there. These are possible consistent definitions of string theory. We've hit upon one set of possibilities. I'm going to try to get more.
These are not the only.
These are not the only ones.
So far we have not discussed open string. So in both type 2 and 2b, the open string content is the same?
No, it can be very, firstly, only type 2b in certain sense can have open strings in all of space-time.
Okay.
Both theories can have open strings on submanifolds, D-branes, and they have very different kinds of D-branes. We will get to that. We will talk about it in detail. Okay? Yes, so there's actually a long way we have to go still. I hope we get there by the end of the semester. But right now let's focus on the closed strings. The open strings in some sense will be derived quantities, as you will see. That's why we're focusing first on the closed strings. Okay, great. But we got all of this assuming that there existed an NSR sector, or RNS sector maybe, RNS sector. Okay? By the way, existence of an RNS sector is the same as the existence in space-time of fermions. Fermions. You see, because R sectors are in spinorial representations. NS sectors are in vectorial representations. Product of vector times spinor representations are spinor type representations. Therefore, yeah, but spinor vector is also vector. Okay? So, these are all the theories that contain fermions, space-time fermions. There may, in addition, be theories that don't contain space-time fermions. And those are the ones we're going to look for. Okay. So now let us look for theories with.
If we just sort of take like the right-hand side of this, is that also consistent? In other words, just have NSNS and RR.
Right. If we just had NS, NS and RR, good. Yes. If we just had NS, NS and RR, that would basically satisfy every requirement we're interested in, and that's actually what we're, but wait, I'm going to get more, just a minute, just a minute, just a minute. Yeah, why doesn't that close by itself? Why doesn't that close by itself? Why doesn't that close by itself? This is a good question. I was going to try to go towards that case, but I get this is a bigger spectrum. Yeah, just I'm trying to understand. Yeah. It solves all the conditions that we want, but turns out not to be modular invariant. Yes. In fact, the things that I'm going to give you, the things I'm just going to assert, and then we'll see when we study modular invariance. Okay. The things that I'm going to give you are an enlarging of your sector to make it modular invariant. Okay, so Yankee's point is a very good one. Yankee's point is that any of these by itself satisfy all the constraints that we've talked about so far. But it turns out that this is not modular invariant. In fact, you can probably quite easily see that. We will see it in detail very soon. Okay. It's basically let's try to see that.
I just have a question. Actually, this question is little vague, possibly. So, all the string theories are known to be related to each other by string dualities.
Yes.
So, in the case where you have string theory where you have which is manifestly chiral and which is not. So, I just want an idea of how the duality could relate.
How could a duality relate a theory that is chiral and a theory that is not? You know, the duality that most simply relates it is T-duality. And T-duality consists of taking the theory and putting it in a circle. Now, whether or not you had a chiral theory before you put on a circle, the theory after you put on the circle is always non-chiral. Okay? So once you take 2B theory or 2A theory, put it in a circle, you get a non-chiral theory. Yes. Basically because in a chiral spinner from the point of view of the 9-dimensional spinner and an anti-chiral, it's the same thing.
Yeah.
Okay? So, the relationship is between these compactified theories, and then taking one side to infinity decompactifies. That's a complicated limit. You know, it involves lots of winding modes on one side. Not just something complicated happens. The simple statement is that they really equal one's compactified, and then there's no contradiction. Okay, yeah, but a good question. Okay, so let's proceed more systematically. We're going to basically get to Yankee's conclusion. Okay, so now let's suppose that there's no RNS sector. This means there must be at least one RR sector. Now we've seen that R plus right. Okay, so let's take any of these RR sectors that do exist. Let's say this one. So R plus, we always have an NS plus, okay. Let's see the full thing and then we'll look at modular invariance because then we'll see the difference. Okay, now this thing by itself is consistent under closure but is not invariant under modular invariance. The thing that makes it invariant under modular invariance is to add in also an R minus sector. Firstly, let's try to see what other R sectors we can add in.
What would be an R minus R plus?
You can't add in an R minus R plus. You see, because the phase with R, for R plus with R minus is minus. So if you have R plus with R minus, that works because of minus into minus. Okay? R plus with R plus works. But R plus with either R minus R plus or R plus R minus would not be mutually local.
Yeah.
So these two at the ends are not mutually local?
These are mutually local because there's a minus 1 times a minus 1.
They add up.
You see, the left moving part gives you a phase of minus 1 and the right moving part gives you a phase of minus 1. Had it been R plus R minus, then there would have only been one minus 1 phase. So suppose we put in another RR sector, this is the only one we could have put in. Once we have this, we are, yes, exactly. Then we also have to take the OP of this with this. And that gives us NS minus. And now the OP closes. Okay, for instance, NS minus with NS plus is NS minus, with R minus is R plus, and so on. Okay?
Basically two Z2s. Yeah. Minus plus NS.
Similarly, you could take this part and complete it. Adding another, you see, modular invariance will require a second R sector. Okay. Now, here if we have R plus R minus, the only other thing that's allowed is R minus R plus.
Yeah.
Okay. So the thing that would complete this would be NS plus, let's write it, R plus R minus with R minus R plus.
And then we would have a contradiction because we would have an NS minus NS plus.
Let's see. This will give us NS minus. And NS plus.
No, I mean if we were also to include the NS plus NS plus.
Also
I'm sorry.
This is just fine.
Yeah, this is consistent, yes.
Okay. And the other two will be plus minus flips of this.
Yeah.
Just one minute. This plus minus can be considered as putting a minus 1 to the power f in that. Suppose I want plus, all that let's say even number of fermions.
Right.
That can be calculated as 1 plus minus 1 to the power f kind of traces.
Correct.
That means this minus 1 to the power f can be considered as changing the periodicity in the time direction.
Correct.
And now we can use the usual rules of modular.
Modular invariance. That's what we do. That's what we do. Exactly. Exactly. So now let's check modular invariance and then let's go home for today. Or at least naively check modular invariance. I'm going to do some naive checks. We'll do serious checks next class. No, I may be writing formulas next class. Okay, so let's first try this. Suppose we just had R plus and NS plus. Okay, so what is this? This, now we have to, this plus, as Indranil said, plus means when you have a plus, it's trace. So say R plus is a trace in the Ramond sector with 1 plus minus 1 to the power FL by 2 and 1 plus minus 1 to the power FR by 2. Okay, so suppose we took this. Now, how I have to translate it to diagrams. So let's translate it to diagrams. So there are 4 terms you can see from here. So it's 1/4 times. Let's see the first term. The first term is minus. That left moving is antiperiodic, right moving is antiperiodic, because trace is automatically antiperiodic for fermions. Okay? Times plus. Okay? Plus, and now this will flip. So you see we'll have 4 terms here. Plus, minus, plus, minus, plus, plus. That's what this first term is.
This is like sum over a single twist sector of an orbital. It's plus twist sector.
Plus twist sector. I would say, well, I don't know if you what to call that. This is like untwisted.
Yeah, this is like untwisted sector.
Untwisted, if you want. It's a sum over all projections in the untwisted sector. Yes. Yes.
That's what I was like,
That's what you want.
Twisted in this case.
Yeah.
Okay,
But you know it's obvious already that we're not going to get a modular invariant. Because you see, what we're going to get is 4 things here. Here we've got only 1 thing, and we're going to add 1 more. But only 2 things downstairs. Okay? So let's write the downstairs way. The downstairs way was ns plus.
If we complete it from orbital perspective, are you going to get this whole sector?
Exactly. So this will be minus. It'll be exactly the same, except this is replaced by minus. You see, because these are also plus. So you continue to have the 1 plus f left into 1 plus f right. So you'll have minus plus minus plus plus, except that everything at the bottom is minus. Sorry, my pluses and my pluses may look similar. I'm sorry, you understand, right?
That's a minus plus, right? And the third one.
This is a minus plus, thank you. Okay, now it's obvious this is not invariant under S duality. What do you have to do to make it invariant under S duality? Well, on the vertical side, you had 4 cases. Minus, plus, and plus. On the horizontal side, you had 2 of these. You had the plus, you had the minus. What you didn't have is the plus and the minus. So what you want is the plus and the minus.
But you have R minus.
Yeah, you have R minus. So that looks, you say, like, okay. Yeah, maybe it's more. Let's write it out. You know, the net thing, yeah, sorry, it's not going to be that. What the net thing is going to be minus 1 to the power FL plus FR. That will be the actual projection. Okay, I'll tell you what we're going to get and then we'll check it. It's not, sorry, I said it wrong. Yes, it's not. It's like a diagonal projection. Yeah. Instead of like minus 1 to the FL and minus 1 to the FR, it will be minus 1 to the power F left plus FR. Yes. In fact, let's check that. You see, what's happening here is that while individual guys can be either pluses or minuses, left FL plus FR is always positive. Minus 1 to the power FL plus FR is always positive. So I'm claiming that what we get is the projection is with -1 to the FL plus FR, and it's going to be modular invariant. So let's try it out. Okay, let me try the following. -1 to the power FL plus FR in fact, I think it's obvious. You see, okay, let's see what if we put the projector -1 to the power FL plus FR. Let's see what we're going to get on the vertical sides. Okay, if we put the projector -1 to the power FL plus FR, what we'll get is this. We will get minus minus plus plus plus, because it switches both FL and FR. Okay, and I want to do that separately in the RR sector and the NSNS sector. But RR was plus plus.
What are you doing? 1 plus this operator and then trace? What is the
Well,
final?
I'm claiming the following. I'm claiming that that thing is trace in NSNS of 1 plus -1 to the power FL plus FR by 2 plus trace in RR 1 plus -1 to the power FL plus FR by 2. Okay, firstly that this is equal to this is obvious. Why is it obvious? It's because we either have both NSNS or RR, that's what we're seeing, NSNS or RR. Now we don't have NSNS and RR uncoordinatedly. We have only those NS sectors such that the FL plus FR is equal to 1, which is the statement. Okay, and then we have this statement similarly in the RR. So that if we want the partition function for that content, it's this. Okay, but now this is simply minus 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 and NSNS, so that's minus minus plus 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 into minus minus plus minus minus into plus 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 into plus plus. Now it's obvious. You see, on both the verticals and the horizontals, we're spraying minus minus and plus plus. So it's clearly symmetric, at least between interchange of space and time.
But the diagonal one wouldn't work.
The one Yankee suggested clearly doesn't work, because there were 4 things on this on time and 2 things on space.
Is this a proof of modular invariance, or is this like a sense like a?
It's a necessary condition. Okay, this is actually a proof of the S duality modular invariance. Okay, there's the tau goes to tau plus 1,
Which you can check still here.
which you can check still here, but you have to do it a bit. Actually, in this case, it's almost trivial. But in the type 2 case, it's a bit subtle, because it cares about the 0 point energies. About these the shifts. We're going to do this in detail next class, so hang on for that. There it will matter that we had. You see, at this level, the argument doesn't care about how many fermions there are. But the actual modular invariance will care about having 10 mod 8 fermions.
10 mod 8?
Meaning, if we have 10 fermions, which we do, it works.
Okay, okay.
If we had 18 fermions, it would also work. Okay.
Two also.
2, yeah. Yeah, 10 mod 8 or maybe 10 mod 16. Anyway, 10 mod 8 is what I remember. As we'll see it. Maybe 10 mod 16. So some phase has to cancel.
That period is.
Yeah. It happens all the time, right? That's the same thing, basically. Okay, so you will see that there are subtleties associated with basically.
Exactly the dimensions at which you can define a Majorana, that kind of spinner.
That kind of.
Majorana line.
It's the same kind of thing. You see mod 8 periodicity in many different parts of physics. Sometimes it becomes mod 16, right? Yeah. Okay, yeah, it's that same kind of thing. We will see this. We will see. But if it doesn't work at this level, it cannot work. At the level of these diagrams, it has to work, and then there may be something more.
So this is doing the tau goes to -1 over tau transformation?
Exactly. And that, though it looks like it's the contentful part of you see the danger here. Actually, this part is sort of more or less guaranteed to work because you're treating the left and the right moving fermions together. The danger when we separately act on left moving and right moving fermions is that we're breaking diffeomorphism invariance in some subtle way. For instance, in some gross sense, if the left moving central charge and the right moving central charge were different, it was impossible to make the theory diffeomorphism invariant. Okay? To regulate the theory, if you regulate with a Pauli-Vilas regulator, you add a mass. That requires you to treat left and right in the same way. Okay? So there is a danger when you treat, you become too abstract. You treat the left movers and right movers as if they're totally separate. That there's no regulator that will give you this result, a good regulator. And we will see that at work. Okay? This kind of thing where you're treating left plus right, you're usually on safe ground, these kind of. Nothing really subtle happens here. This would work in any dimension. It's the type 2 thing that is more subtle because it's left and right separately. Okay, so I shouldn't, before ending, I should give you a few names. This thing is called type 0 theory. And once again, the guys where you've got minus are the chiral thing. So this is called 0b theory. And this is called type 0a theory. Now, type 0a and A theory and type 0b theory, we have already said that they do not contain space-time fermions. Much worse, they contain the ns minus sector. Now, why is that bad? ns minus sector in the matter includes identity operator, and therefore it has a tachyon. So these theories are tachyonic. Something I did not perhaps emphasize, but I should emphasize now, is that none of these type 2a and type 2b theory contain an ns minus sector. The ns sectors were always ns plus. Identity operator does not lie in this sector. The matter identity operator does not lie in this sector. Okay? And therefore, note that identity operator of the full conformal field theory, matter plus ghost, always lies in ns plus. But the point was that we were forcing the operator in the vacuum sector to be e to the power minus phi. So it's better to say e to the power minus phi does not lie in that sector. That was the potential tachyon. And the fact that we've removed it means that these theories are tachyon free, as we will see in more detail. Okay? So we've finally managed to construct tachyon free string theories. Okay? Through these elaborate maneuvers. Okay? We have 1 or 2 more formal lectures left. 3 or 4 more maybe, I have to tell you with the heterotic string. Okay, maybe 3 or 4 more formal lectures left. I'm done, Kapil, sir. Yeah. I have to tell you about the BRST, charge for this, for these theories. We have to understand the rules for scattering amplitudes. And then I have to tell you about the heterotic string. And then after all of this, we'll actually go back and start doing calculations. We'll then start trying to understand the physics of these theories. It'll be more fun than this kind of stuff.